Hey guys, welcome back to Genius Learning. So in this video, I want to derive the range equation for a projectile motion using the kinematic equations. All right, so let's start off with a picture of what we're going to be talking about. So we got y, x, right, and this is 0. Let's say we have some type of cannon. All right, and it fires a projectile, right, at an initial velocity. Remember that vector symbol. It goes all the way up, some max height, and then it comes back down. Let's say it hits right there. All right, it should be a perfect parabolic shape, but I suck at drawing right now, so let's just extend it. Okay, and maybe we'll pretend this never happened. So don't mind this part. It should be a perfect parabolic shape, so the same shape on both sides. So, okay. So now, and let's extend this x hat. To avoid confusion, let's just do it over. Okay, so we got some cannon, right, firing a projectile with a initial velocity, and we go up, and all right, that's better, and we land there. Okay, so now let's see the conditions that we have. So t equals 0, which is here. We have no acceleration in the x. We have always acceleration in the y, which is gravity. So that's one thing that we have to kind of understand. So let's start off with this, breaking up the velocity vector. All right, so what we're gonna do is this right here, we want to break it up, and here we have that same velocity initial vector, right? But I want to describe it in, let's put vy, vx. I want to describe this initial vector, right, as a vector in the x and a vector in the y. So I'm going to do a dotted line here. Right, this is a 90-degree angle. And remember that this is vx, this vector that's going to go along here, and up here is going to be vy, whatever vector is going to go along there. So it's going to be a vector like that for the vx, a vector like that for the vy, because remember that v, we could put initial there. So we can put initial, then this is vx initial in the I hat plus vy initial in the j hat. Okay, remember that j hat is the y and I hat is the x. Okay, just more stuff to confuse you. All right, so we have these two things. Okay, so from the previous examples, I did some of the trig stuff here, and so for the vx, we have v initial cosine theta, and for the vy, we have v initial sine theta. And I'm expecting you to know some trig so we can move past that part, but if you're struggling with that, I have some other videos that go into detail about how to get these. Okay, so we have vx, right, and we have vy, and now we can continue. So I like to use a general formula, okay, and it is the kinematic formula that you're gonna need to remember. It's gonna be very important for most of the calculations you're gonna do for a projectile and other things coming up. So you're gonna have displacement is equal to velocity initial times time plus 1/2 gt squared. And I should put here acceleration, right? And show you what I mean by general. So this is an A. Okay, so now what I mean by general is that this equation here, remember when it doesn't have a subscript, red flag should go off. It's not telling you the whole truth. And so I need displacement in the X, right? Which is velocity initial in the X times time plus 1/2 acceleration in the X times squared, right? Displacement in the X, you can also write this. You can also write change in X is equal to V naught or V0 initial of X times T plus 1/2 acceleration in the X times time squared. So this is the one that we're probably familiar with. So that's one thing that was derived from this. Now we need the second one. And so let's try to get a different color. Now this is for X, right? From this one. And now we need to tell us the Y. So D, or displacement in the Y, which is velocity initial in the Y times time plus 1/2 acceleration in the Y times time squared. Okay, we can leave it like this, but let's take it one simplification further. The displacement in the Y we can put as the change in Y. Okay, velocity initial in the Y times time, right? And then acceleration in the Y is always gravity, right? So the only acceleration that an object is feeling in the vertical direction is going to be due to gravity. So that's another concept you kind of have to harness in, that AY is always going to be negative G. So we're going to change this to negative G. So negative 1/2 G T squared. And see how G does have a vector over it because it tells us that it's going in a certain direction. It's not just going sideways or whatever, it's going directly down, perpendicular. Okay, so these are the two things, the two equations that we derive from this one general equation. So displacement is equal to velocity initial times time plus 1/2 A T squared. We break it up into the X and we get our X kinematics, displacement, and then we get our Y displacement equation and move forward. So next, okay, we got, let's make sure you can see, and of course you can't. All right, so now we got these two equations. Let's write them out in the front. Let's see. Okay, I'm gonna put them here. So I'm gonna have the X one, change in X is equal to velocity initial in the X times time plus 1/2 acceleration in the X times squared. Okay, and then the Y, I'm gonna write the change in Y, velocity initial in the Y minus 1/2 G T squared. Okay, so now I meant to kind of separate these, so stay on your side. All right, so now let's analyze this side first. Okay, I throw the ball up, right? And there's no acceleration in the X direction, because the only acceleration that would be in the X if it was applied personally. If I kick the ball in this direction or you know, there's a wind, there's an external, you know, force applying an acceleration in the horizontal. Unless that's happening, which is usually not the case, especially for physics 1, then acceleration in the x is always 0. Most of the time, for physics 1 purposes, it's mostly always 0. So always be on the lookout. Unless they give you and they say acceleration in the x is a certain value, this is 0. Okay? Just like we did, acceleration in the y is negative g. That's always the case, always. This one, most of the time it's 0. Very rarely they'll give you a number. So just watch out for that. Now the second thing we're gonna do with this is change v initial in the x, because we know that v initial, right, in the x direction is this right here, right? We got the v initial, but the v initial in the x is equal to v naught cosine, or v initial cosine. So I'm gonna write the change in x is equal to, instead of v initial x, I'm gonna write v initial cosine theta times time. Okay, and then I'm gonna leave that right there. Okay, this is the displacement in the x. Now, on this side, let's also do the same thing, all right, and change up v initial in the y, because we know that it's v initial sine theta. So the change in y is equal to v initial sine theta times time minus 1/2 gt squared. Okay. So now we have the change in y, kinematic equation written out. Okay, so now let's do another thing. So in order for us to, let's move this a little over here. So in order for us to go from here to velocity, right, we're gonna need to take the derivative. All right, so we can also do, it another way. So if derivatives make you uncomfortable, let's just do it with logic. All right, so let's do this. This ball or object is gonna go all the way up, right? Max height, and then come all the way back down here, right? So the change in y, right? y2 minus y1 is gonna be 0, because y2 is gonna be up here, y2 is gonna be here, sorry. And so y2, your last height is gonna be here, and your initial height was at the same place. So this is gonna equal 0, right? So it's gonna be 0 right there, right? Because you're starting at an initial height of 0, and then you go and you finish your trip, and then your height at the final distance is 0 also. And so this side is 0, and then here, v initial sine theta time minus 1/2 gt squared. Now we can cancel out one of the t's. Okay, and let's solve for time. And remember that this time here now is described as t final. So I'm gonna write t final. That means that's this time right here. And we'll say like this piece is like time max height. So just to note the difference. So time final is this one, and now we have to change it since we used the condition that all the way at the end of the range, right? So let's write something else here. Okay, so the condition was that we want the range equation, right? And the range is specifically when the projectile is launched from a certain ground level and reaches the ground level again. So the displacement in x could be anywhere in between here. You know, you could say x2 is here, x1 is here, But if you talk about range, range is only from ground level all the way to the end where it meets the ground level again. So that's the difference between range and the change in x. So the range has a condition in the y that both y's are in the same spot, meaning the change in y is 0. Because of that, we have to change t to t final. Right? That's the maximum time. This is the max height. This is the maximum time that this thing is gonna take to get to that side. All right, so now let's solve for t final. So we have here, I'm gonna pass, let's do this in maybe 2 steps. So we're solving for time final. So I'm gonna pass this to the other side, get rid of the negatives. So v initial sine theta is equal to 1/2 gt final squared. I'm gonna pass the 2 over, divide by g. So 2 v final sine theta divided by g, and then square root everything, and that's equal to time final. So make sure you guys could see. Okay, so that's time final. All right, and let's box this up because we're gonna need this now. Okay, so realize that from the kinematics of the y equation, we were able to get time final because we're looking for range. That's the whole goal of this. And the range has specific conditions for the y side, where the range is only described from the ground level all the way back to ground level. And so the change in y is 0. Taking advantage of that, right, we can solve this equation for time at maximum, the max time. So the final time, the max time, okay? And we solve for t final. Now, if we want to describe the range on this side, then this change in x must describe the range, not just a random x value. So x2 minus x1, x2 could be anywhere in here, but if we're talking about range, which is what we want to find, then it makes sense to plug in the t final, like the maximum time that this thing is gonna spend in the flight and all the way back down, into here. So now you've changed your change in x to range because it's describing when it comes back down all the way to the ground. It's a specific thing. So v initial cosine theta, and then we have the square root of 2 v naught sine theta over g. And let's see. Oh, so this 2 was not here. So here we canceled out the 2. And so this 2 does not exist. It almost got me. So this does not, oh, that's not gonna work. Okay, so here when we made this 0, one of the t's canceled and this one was squared and it was canceled, so there's only 1. And so this is not squared and there is no square root. All right, so no square root. All right, just this inside of those parentheses. Sorry about that. All right, so now let's write this range equation down here. And remember, this change in x can be the range if your second value, like x2, is all the way where the projectile comes back down. So this could describe the range if we're talking specifically about ground level and come back to ground level. But range is that definition. So since we use the time final, we're gonna change the notation to range, which is what we're looking for anyway. So let's see. we got, I'm just gonna rewrite it. R is equal to this V naught and this V naught are gonna be V naught squared. I'm gonna pull the G towards the front, and then I'm gonna have here 2 sine theta cosine theta. If you look at this and bells and alarms and whistles didn't go off, then you need to review trig, because this is an identity, and the identity is sine of 2 theta is equal to 2 sine theta cosine theta. So trig is important. It's going to come back to haunt you in this class if you don't just review it. Changing this to this identity, now we can make this a little more elegant. And let's choose an elegant color. I'm not sure if this is elegant, but we're going to change this now to the identity, and we have finally range is equal to V initial squared over G sine of 2 theta. Let's see if you guys can see that. Yeah, perfect. Right, so yeah, that's it. We're gonna have a projectile being fired out. Let's see if we can see. Okay, so we got a projectile being fired out of the cannon, right, at the ground level. It goes up to a max height and then comes back down, perfect parabolic shape, to a time final, and y final, which is the same as the initial. Okay, so that condition right there, let us say that, you know, the change in y is 0. So before that, we look at the velocity components, and we associate them. You know, Vy is equal to V initial sine, Vx is equal to V initial cosine. Okay, we do that first, then I use this displacement equation, which is just 1. I find it easier to just always write this and then break it up into 2. So this displacement vector doesn't have a subscript, and so it's not telling us the whole truth. I need to know the x direction and I need to know the y direction. So in the x direction, right, ax, acceleration in the x is most of the time 0, unless given to you in the problem. And then the displacement in the y, the acceleration in the y is always gravity, negative gravity. So we're gonna change this equation that has like the y's in it, and we're only gonna change this part that is gonna have negative g. And for this one here, we're gonna make this 0. So I've taken these two and I wrote them side by side. And so we're gonna work individually, right? We're gonna start off with, I think we started off with this side. So for the x, displacement in the x, right? Acceleration in the x is 0. So now we're just left with this equation, and we're gonna hold on to that, right? And then let's work on this side now. So we changed V initial y into its component form, which is V initial sine. And then this was already changed, the gravity. So let's apply the condition. And the condition comes from wanting to find the range. So the range specifically defines something that is ground level and comes back down to ground level. All right, and so because of that, the change in y is equal to 0. Time maximum, right, the time final is applied now, because that's the specific time that we're talking about. And changing those things, or applying 0 here and the time final, we're able to cancel one of the times out, and solving for time final, we get this value right here, 2 V naught sine theta over G. So now we have the time that specifically describes all the way at the end of the trip. All right, so now we plug that in to what we were holding before, which is the change in x, plugging in this time final into this equation changes what we define our change in x in. Now, the change in x can't just be anywhere along here. It has to be all the way at the end where the projectile comes back down, because that's what range is. And since we're using time final, range is what described this time final to begin with. And so now we change the change in x to range, v naught cosine, and we plug in t, all this stuff in here. All right, so putting things together and looking for identities, we find that this is equal to sine 2 theta. When we change that, then we get a nice elegant definition for range. So range is going to equal v initial squared over gravity sine 2 theta. Okay? All right, guys, hope that was helpful.